Okay, hi folks, welcome back, and hot on the heels of the SQA publishing this year's papers on their website, it's time for us to go over the 2024 National 5 multiple choice paper. It's also available on the Colleglen High School Physics webpage. Just click on National 5 Resources and then scroll down to Past Papers, click on Past Papers, and there it is at the top of the table. There's paper 1 there and paper 2, and the marking instructions are on the right hand side. But we're going to go through the multiple choice questions. That's section 1 of the paper. And remember, the whole paper is 2.5 hours, but the multiple choice section should probably take you about 40 to 45 minutes. We're going to see if we can do it in about half an hour. So first thing you see, as usual, is the datasheet. That contains all the numbers that you might need as you work through the paper. And then on the next page we get to the start of the multiple choice section. Now, make sure you go over these yourself first and then come back when you're ready and you can see how we have done them. The first 10 questions or so are from dynamics and space, and question 1 is about scalars and vectors. So question 1 says, which row in the table classifies speed, weight and energy correctly? Well, you should know at National 5 that a measurement that requires a direction for it to be fully described is called a vector. And there are 5 vectors that you need to be aware of at National 5 Physics, and they are displacement, velocity, acceleration, force and weight. All the other quantities that you meet in National 5 Physics are called scalars, because a single number is all you need to fully describe the magnitude of that quantity. So if we are asked to classify speed, weight and energy correctly, then the only one of them that is a vector is weight. So speed and energy must be scalars then. Let's highlight them first then. So speed is a scalar and energy is also a scalar, but weight is a vector. And then the only row in the table where everything is highlighted is in answer E. So that's 1E. Question 2. A student uses the apparatus shown to determine the average speed and the instantaneous speed of a trolley as it travels down a slope. And the trolley is released at X and travels down the slope. And the distance between X and the light gate at position Y is labelled on the diagram with the letter D. The time taken for the trolley to reach the light gate is T1, and that's shown on one of the stop clocks. The length of the card on the trolley is L, and the time taken for the card to pass through the second light gate is T2, which is shown on the second timer there. And then we're asked, which row in the table shows the measurements required to determine the average speed of the trolley between X and Y and the instantaneous speed of the trolley at Y? Well, average speed is the total distance gone divided by the total time taken. And the instantaneous speed at the bottom of the slope, you would calculate from the length of the card divided by the time it takes to cut the light beam. So that's L divided by T2. So then looking at the answers for the measurement for the average speed between X and Y, we need the total distance gone, that's D divided by T1. And there's 2 options there for us, B and E. The instantaneous speed at the bottom of the slope, we would use the length of the card and T2. And again, there's 2 options there we could use. But the only row that's got them both highlighted is answer B. It's pretty tricky. Question 3. A rocket is taking off from the surface of the Earth, and the rocket engines exert a force on the exhaust gases. Which of the following is the reaction to this force? Well, from Newton's third law, every action has an equal and opposite reaction. So if the rocket engines exert a force on the exhaust gases, then the gases must exert an equal and opposite force on the engines. Any mention of the earth here or the ground here is incorrect, and all the other answers talk about the force on the earth. So it's answer E. Okay, question 4. A motor raises a mass of 2,400 kilograms vertically through a height of 5 metres in 2 minutes. And we have to work out the minimum power rating of the motor. Well, the relationship we're looking for here is P equals E over T. And we know that the time is 2 minutes. But we don't know what the energy required is to lift the mass. But the clue here is that we're lifting a mass vertically through a height of 5 metres. So we can work out what its gain in gravitational potential energy is. EP equals mgh. And if we sub in for the mass, 2,400 kilograms, G on Earth is 9.8 and the height is 5 metres. And if you do that on your calculator, it'll give you an answer of 117,600 joules. And I'm not rounding that because we're going to sub that into the power relationship. So it's 117,600 divided by 2 minutes. And watch out here, you've got to change the 2 minutes into seconds. So 2 minutes is 120 seconds. And then that gives you an answer of 980 watts. And that corresponds to answer B. And watch out, because if you don't change your time into seconds, then you'd get an answer of 59,000, which is a wrong answer. That's sneaky. They always put the right wrong answers in. Watch out for that. Question 5. A satellite is in circular orbit around a planet, and a group of students make the following statements about the satellite in orbit. So statement 1. The horizontal speed of the satellite is constant. By horizontal, I think they mean parallel to the surface of the Earth, in which case that statement is correct. And statement 2, the satellite doesn't move. Well, yes it does, it's orbiting the planet, so it's always moving, so that one's wrong. Statement 2 is incorrect. And then statement 3, while orbiting the planet, the satellite is weightless. Well, it's still in the Earth's gravitational field, and it's the pull of gravity that is keeping it moving in a circle around the Earth. So technically there is still a force on it due to gravity, so it still has weight, but the satellite and everything on it will appear to be weightless because it's in free fall as it moves around the Earth. It's always accelerating towards the Earth, but never gets any closer to it. Very difficult. I think statement 3 is incorrect. So therefore the answer must be one only. That's 5A. That's really tough. Didn't think we did general relativity at National 5. Anyway, let's move on. Question 6. A pulse of light from a laser is transmitted from the Earth to the Moon, and the light reflects from a mirror on the Moon and is detected back on Earth 2.6 seconds after being transmitted. So the distance from the Earth to the Moon is, well, we're going to use distance equals speed times time here, or speed equals distance over time. In fact, let's rearrange it first. Distance equals speed times time. It's a pulse of light, so the speed we're going to use is the speed of light, 3.0 times 10 to the 8. Now it's the distance from the Earth to the Moon we want, and it took 2.6 seconds to go there and back. So the time it took to reach the Moon was only 1.3 seconds. And if you do that in your calculator, you get 3.9 times 10 to the 8 metres. That's answer D. And again, watch out here, because if you forgot to half it, then you would have got 7.8 times 10 to the 8. Sneaky. Question 7. Table shows the altitude and period of 4 satellites. Altitude is the height above the Earth's surface, and the period is the time it takes to go round once. So we're looking for the period of APRIS-SAT 3, and if we look at the pattern of the numbers, the lower the altitude, the shorter the period. So if the altitude is 686, we're looking for a period that is just greater than 95, and so the only one I think we can pick is 98 minutes. The greater the altitude, the longer the period. So 7C. Moving on, question 8. The student makes the following statements about the universe. Statement 1. 1 light year is the time taken for light to travel from the sun to the Earth. That's a lot of nonsense. A light year is the distance that light travels in a year. Statement 2, the approximate age of the universe is 13.8 billion years. That's correct. And statement 3, the Big Bang Theory describes the origin of the universe. That's correct as well. So 2 and 3 are correct. That's answer D. Then moving on to question 9. And question 9 is the start of the electricity questions. An electric field exists around 2 point charges Q and R. And the diagram shows the path taken by a charged particle as it travels through the field, and the motion of the particle is as shown. I've seen this diagram before. I think it's been in a couple of past papers before this. Anyway, which row in the table identifies the charge on the particle, the charge on Q and the charge on R? Well, the thing to notice here is that the particle is moving across the page from left to right, and as it passes particle Q, it's attracted down towards it, and then as it passes particle R, it's also attracted around particle R and then moves on its merry way. So, as you know, opposite charges attract each other, so therefore the particle must be the opposite charge to both Q and R. So if the particle was positively charged, then Q and R must be negative. And that's answer A. The only other possible answer is that the particle could be negative and Q and R could be positive, but that isn't one of the options. So it must be 9A. Alright, moving on, question 10. A toaster is connected to a 230 volt main supply and switched on, and the heating element in the toaster has a power rating of 1.2 kilowatts, that's 1200 watts, or more importantly it uses 1200 joules per second. And the student makes the following statements about the toaster. Number 1, the heating element transfers 12,000 joules of electrical energy each second. No, it doesn't. It's 1200 joules per second. Statement 2, the plug of the toaster should be fitted with a fuse rated at 13 amps. Yes, it should, because anything over 700 watts should have a 13 amp fuse in it. And statement 3, the charge passing through the heating element each second is 230 coulombs. I don't think so, but we need to do a calculation to figure this out. So let's use Q equals IT to work out the charge, but we don't know what I is. But we can work out I using one of the power equations. I equals P over V. We know what the power is, it's 1200 watts, divided by the voltage 230 volts, and that gives us a current of 5.22 amps. And remember, current is the amount of charge that's flowing per second. So in a time of 1 second, the amount of charge that flows is 5.22 coulombs. So statement 3 is wrong, and that means the only one that's correct is statement 2. So the answer to question 10 is 10B. Pretty tricky. On to question 11. A circuit is set up as shown, and the reading on voltmeter V1 is 3.6 volts. And we have to work out the reading on voltmeter V2. Now, this is a voltage divider circuit where the two resistors are sharing the supply voltage, and some of the voltage, in this case 3.6 volts, is across the top resistor, and some other voltage will be across the bottom resistor. And we've got a relationship we can use to work out what V2 is. And there it is, V1 over V2 is equal to R1 over R2. In other words, the ratio of the voltages is the same as the ratio of the resistors. So let's put in the values that we know. V1 is equal to 3.6 volts. That's over V2, which is what we're looking for. And that'll be equal to the top resistor, which is 16 ohms, over the bottom resistor, which is 24 ohms. And we're looking for V2, so that's quite tricky to rearrange. So what I'm going to do is just flip the whole lot upside down. So V2 over 3.6 will be equal to 24 over 16. And then if we multiply both sides by 3.6, that means we lose the 3.6 on the left hand side and it appears on the right hand side. And then if you do that on your calculator, It gives you an answer for V2 of 5.4 volts, and that corresponds to answer E. Question 12. A circuit is set up as shown. It's a mixed series and parallel circuit with an LDR in it, and the resistance of the LDR increases as the light level decreases. You may have seen or heard the acronym LURD here for this sort of circuit, which stands for as the light level goes up, the resistance of the LDR goes down. But in this case, the light level is decreasing, and so the resistance of the LDR will go up. But Ludaroo doesn't have the same ring to it, I suppose. Anyway, light level incident on the LDR decreases. Which row in the table describes the effect of this change on the readings on the ammeters? Well, the resistance of the LDR is going to go up when the light level decreases, and if resistance goes up, then the current is going to decrease. So A1 is going to decrease, and if the total current decreases, then the reading on the other two ammeters must go down as well. So all three ammeters decrease, and so the only possible answer then is answer A. Moving on to question 13, three resistors are connected as shown. There's three resistors in parallel, and we have to work out the total resistance between X and Y. So we need to use our relationship for working out the total resistance in parallel. And 1 over the total resistance is equal to 1 over resistor 1 plus 1 over resistor 2 plus 1 over resistor 3. And the easiest way to do this is to use the fraction button on your calculator. And depending on what kind of calculator you've got, the layout of the buttons might be slightly different, but the button you're looking for here is the fraction button, which is second top on the left hand side of my trusty Casio FX85 GTX. So if you press the fraction button, then you can just type in your sum. So 1 over 12, cursor to the right, plus another fraction, 1 over 6, cursor to the right, plus another fraction, 1 over 4, cursor to the right, equals, there's your answer, but that's 1 over the total resistance. So you've got to flip it upside down, so you press the X to the minus 1 button, and there's your final answer for the total resistance of those three resistors. It's 2 ohms. Now your rough working isn't marked in a multiple choice paper, but I would encourage you to do as much rough working as you need to do to get the answer that you require. And in a final exam you can do that rough working on the question paper, or there's space for working at the back of the booklet, but I would always do it on the question paper beside the question that you're doing. Anyway, if for some strange reason you would rather do this the long way, then you can still substitute the values in, having a lowest common denominator in your fraction calculation. So it would be 1 over 12 plus 2 over 12 plus 3 over 12. And then you can add all them together. That gives you 1 plus 2 plus 3 is 6 over 12 is equal to 1 over 2, and then flip it upside down to give you RT is equal to 2 ohms. But much easier, just do it on the calculator. So 13B. Question 14. A length of wire has a resistance of 8 ohms, and the current in the wire is 1.5 amps, and the power developed in the wire is, well, we need a relationship here for power that's got current and resistance in it, so it's P equals I squared R. The current's 1.5, don't forget to square it, times the resistance is 8 ohms, gives you 18 watts, so that's question 14C. Question 15. A student carries out an experiment to determine the specific heat capacity of copper, and the setup used by the student is shown. And hopefully you've done this experiment in class. If not, then I have a very similar experiment on this channel to work out the specific heat capacity of a metal. Anyway, the student heats the copper block for 5 minutes. The temperature of the block goes up to 14 degrees, and the value of the specific heat capacity of copper determined by the student using this method is found to be inaccurate. And if you have done this experiment, you realise that the value that you get for the specific heat capacity of copper is much higher than expected, because you're losing heat energy out the sides of the block to the air that's in the room. And the only way to make it more accurate is to place insulation around the copper block to try and reduce the amount of heat energy that's escaping. So the answer is B, place some insulation around the copper block. A lot of reading in that question, but a kind of common sense answer there. Question 16. A solid substance is placed in an insulated container and heated. Sensible pupil doing the experiment this time. The graph shows how the temperature of the substance varies with time, and to determine the specific latent heat of vaporization of the substance, a student should use the time from section. Well, if we follow the graph up from where it starts at point P it's a solid, and we heat it up to point Q, and then it starts to melt, it becomes a liquid at point R, then we're heating up the liquid until point S, and then from S to T it's turning into a gas, so that's when it's vaporizing. So between S and T, where the graph is flat because there's no temperature change when the state is changing, then that is where we should measure the specific latent heat of vaporization. So S and T, that's answer D. Question 17. A syringe containing air is sealed at one end as shown, and the initial volume of the air in the syringe is 1.4 times 10 to the minus 6 cubic meters, and the pressure is 120 pascals. The plunger's pushed in, causing the volume to be reduced by 0.3 times 10 to the minus 6 cubic meters. The temperature stays the same, and we have to work out the new pressure inside the syringe. So first things first, make a little list of everything you know from the question. So the first pressure is 120 kilopascals. That's when the volume is 1.4 times 10 to the minus 6 cubic meters. The second pressure is what we're looking for when the volume has been reduced by 0.3. So it will go from 1.4 down to 1.1 times 10 to the minus 6 cubic meters. Then we're looking for the relationship between pressure and volume. So it's P1 V1 is equal to P2 V2. Sub in your numbers. 120 times 1.4 equals P2 times 1.1. And you'll notice I'm not putting in any prefixes or any powers of 10 because they'll all cancel out once we do the arithmetic. But if you work out P2, it'll be 120 times 1.4 divided by 1.1, and that gives you an answer of 153. And because P1 was in kilopascals, then P2 will also be in kilopascals. 153 kilopascals, that's 17D. Question 18 is a relationship you've never seen before. FB equals rho GV. That funny shaped P there is a Greek letter called rho, and it stands for the density of a fluid. G is the gravitational field strength, and V is the volume of the object in cubic meters. And we have to work out the volume of an object that experiences a buoyancy force of 360 newtons when it's immersed in a fluid of density 1020 kilograms per cubic meter. Well, because this isn't in the course and it's a relationship you've never seen before, all you're required to do here is plug the numbers into the relationship and work out the value for the quantity that you're asked. In this case, it's the volume. So we rearrange the relationship. So V will be equal to FB over that wee curly P times G. And we know what all those numbers are on the right hand side. The force was 360, the density is 1020, and G on Earth is 9.8. And if you do all that on your calculator, then you get an answer for the volume of 0.036 cubic meters. And that corresponds to answer A. Moving on, question 19. We're now on to waves. The diagram represents a wave travelling from X to Y. The speed of the wave is 48 meters per second, and we have to find the frequency of the wave. And before we find the frequency, we need to know the wavelength of the wave. So if you count how many complete wavelengths there are in the 24 metres that is shown there, then there are 3 complete wavelengths in 24 metres, so the wavelength is 8 metres. We can now use our wave equation, v equals f times lambda, and substitute in for the speed of the wave and the wavelength of the wave, and then rearrange it to find the frequency. 48 divided by 8 gives us 6 Hertz, and that corresponds to answer C, 19C. Question 20. The letters X, Y and Z represent missing words or phrases from the following passage. Infrared has a blank wavelength than visible light. This is the electromagnetic spectrum here, so let's very quickly draw an electromagnetic spectrum diagram with visible light in the middle, UV above the violet, infrared below the red, microwaves and radio waves to the left, X-rays and gamma rays on the right hand side, increasing frequency from left to right, and the long wavelengths are at the left, shorter wavelengths at the right hand side. So infrared has got a longer wavelength than visible light, so X is longer. So there's 3 possibilities there. Now what about Y? Infrared diffracts. Now is it more or less than visible light? Well, infrared's got a longer wavelength than visible light, and long waves diffract more. So Y is going to be more. And then for Z, the speed of infrared is it the same as, slower than, or faster than visible light? Well, the speed of light is the same for all the sections of the electromagnetic spectrum. And so the only row with them all highlighted is C, that's 20C. And question 21, the diagram shows the path of a ray of red light as it passes through and out of a semicircular glass block. Which row in the table shows the angle of incidence in the glass and the angle of refraction in air? Well, the thing to remember about ray diagrams is that the angles should always be measured to the normal. And the angles that were given on the diagram are measured relative to the side of the block. So we need to find the missing angles relative to the normal. So in air it will be 32 and in the glass it's 20. So the angle of incidence in the glass measured to the normal is 20 degrees. And the angle of refraction in air is 32. That's answer A. Question 22. Which of the following statements describes the term ionization? Well, ionization is when atoms gain or lose electrons, and the only answer with the word electron in it is answer B, the removal of an electron from an atom to form a charged particle. That's 22B. Question 23. In a radioactive source, 1.8 times 10 to the 6 nuclei decay in 10 hours. What's the activity of the source? So the relationship we're looking for this time, activity is the number of decays per second, A equals N over T. The number of decays is 1.8 times 10 to the 6 divided by a time. Now it's 10 hours, but we need that time in seconds. So that's 10 hours times 60 minutes times 60 seconds. And if you do that on your calculator, it gives you an answer of 50 becquerels. And that corresponds to answer E, 23E. Nearly there. Question 24. A sample of tissue receives an absorbed dose of 0.2 micrograys from a source of alpha radiation and an absorbed dose of 6 micrograys from a source of slow neutrons. And we have to work out the total equivalent dose received by the sample of tissue. Well, we've got 2 calculations to do here using our equivalent dose relationship. That's H equals dWr, where D is the absorbed dose that we get. So let's do it with the 0.2 micrograys from the alpha radiation first. So it's 0.2 times the radiation weighting for alpha. Now you'll find that on your data sheet. Little table right at the bottom of the data sheet says for alpha radiation the radiation weighting is 20. So we multiply our 0.2 times 20, and that gives us 4 microsieverts. Oh, I've got 4 sieverts there, I'll change that in a minute. But we also need to do the calculation again for the slow neutron dose. So the dose that we get of slow neutrons is 6 micrograys. So let's put that in. That's the 6 times the radiation weighting for slow neutrons. And again on the data sheet, the radiation weighting for slow neutrons is 3. That gives us an answer of 18 microsieverts. Let's change the 4 as well, 4 microsieverts. Because the absorbed dose was in micrograys, then our answer for the equivalent dose will be in microsieverts. So if we add the two of them together, 4 plus 18 gives us 22 microsieverts. That corresponds to answer C. Last question then, question 25. A technician carries out an experiment using the apparatus shown to determine the half-life of a radioactive source. And before carrying out the experiment, the technician measures the background count rate. The technician takes readings of the count rate displayed on a rate meter every 60 seconds for a period of 20 minutes, and a graph of the technician's measurements is as shown. And then we are asked which of the following changes would allow the technician to more easily determine the half-life of the radioactive source. Well, the graph is showing us the corrected count rate as it was measured over a time of 20 minutes. And 20 minutes isn't enough for that corrected count rate to fall from its initial value down to half its original value. So the change that would allow the technician to more easily determine the half-life of the radioactive source would be to carry out the experiment over a longer period of time. And the only answer that talks about increasing the length of time for the experiment is answer B. Take the readings of the count rate every 60 seconds for 40 minutes. And that would be enough time for the initial corrected count rate to fall to half its original value. And that's it then. That's the 2024 multiple choice paper, section 1. A lot of reading in it, but quite straightforward. If you sat that paper, I hope you did well. If you're revising for a future exam, then I hope that helps. We'll see you in the next one.